This is on distance and displacement. This unit involves kinematics, and that was also the title of the unit, which is basically a branch of physics that deals with describing motion that doesn't consider the forces involved in the motion. And so we'll be looking at distance and displacement, we'll be looking at velocity and acceleration of objects. And we looked at it from the graphing point of view. We're going to be looking at it also from the calculation point of view as well. And so last time we learned a little bit about adding vectors, and now we're going to be looking specifically at what types of vectors can we actually add. So one of those vectors could be the change in displacement over time. It's obviously not going to be distance, because if we look at distance is a measure of how far an object moves without any reference to the direction, aka it's a scalar value. As for displacement describes the change, and often it's described with that delta. So delta is change in displacement. So it's a change in position of an object during a time interval. So from a time of x seconds to x plus however many more seconds there later. It is described by the magnitude and direction of the change in position. It is also known as a vector. When you look at delta over here, that is a Greek symbol. It is used to describe a change in something. So for displacement, it is used to describe a change in position. To use this symbol, always take the final value and subtract the initial value. So this is probably something that that might be a little bit backwards, but just be aware of that. When you are finding the change in displacement, you'll be looking to find what is your final value minus your initial value. And that's going to be your change in displacement. So the final value minus the initial to find the change in it. So you're saying, where did you start and then where did you end up? And to determine, well, what was the displacement over that time period, you take the final value, subtract the initial. When working with specific directions and when working with vectors, directions are very important and must be considered in calculations. So as we mentioned before, when adding vectors, you want to make sure to have not only the magnitude, but also the angle and the direction. So you can get an angle for your final resultant vector, but you also need to then determine, well, in what direction is that angle pointing? Is it north? Is it east? Is it 30 degrees northeast? Etc. Different directions are indicated by positive and negative, and we have mentioned this, but again, please keep in mind that for the majority of the time, unless otherwise stated, positive is always going to be to the upwards direction or to the right. Negative is always going to be down and to the left. When solving a problem involving vectors, make sure to always first indicate which direction will be represented. So again, let's just assume that is going to be true in every case unless otherwise stated. So it's always positive up and to the right, down and to the left is negative. And again, it doesn't have to be down and to the left, it can be down or to the left. A reference point must also be determined before solving a problem. So depending what you determine your reference point to be. So right now this pen might be whatever else, 5 centimeters off the table. It's hard to see that based on what's going on. If the table is the reference point, well then you could say yes, it is positive 10 centimeters from the reference point. But if the reference point was the floor from the table, well, it's going to be the 31 inches from the ground. Or is the table 29? Anyways, that plus this extra 10 centimeters, and that would be what it would be in comparison to the ground if we were using that as the reference point. So just be aware of that. So this has to be a fixed point, and all measurements are made from that location. It's similar to math where you have a number line and you have the numbers in the negative values, you get to 0, and you have all the positive values. So 0 is similar to a reference point in physics. And so you can also think of the reference point if you were standing and watching the movement from a set location, such as a lawn chair on your deck or at the cabin if you're so lucky to get to go to one. So let's try a couple of examples here. The first example is imagine you are in Niverville, so that's probably pretty easy to imagine that. Decide to go for a drive one Saturday afternoon. You drive 8 kilometers south of Niverville. When you decide to turn around and drive 13 kilometers north, perhaps you forgot something or you were really bad with your directions and were attempting to go to your friend's house and went way in the wrong direction there. So 2 types of questions here. Number 1 is what is the distance? And secondly, well, what was your displacement during your travels on that Saturday? So let's start off with distance because it takes a little bit less time. With distance, you will just be adding these two values together. You went 8 kilometers south, then you went 13 kilometers north. So what was your total distance is just adding these two together. And we're going to have 21.0 kilometers. As for your displacement, if we were to draw out our displacement for a moment here, just to visualize it, so we can just write displacement here, but let's visualize it on the side here. You start at some point, our reference point right over here, driving 8 kilometers south. So this represents 8 kilometers south. At which point you went 13 kilometers north. So from the tip to tail, up we go. And if that's 8, and we're going to go with 13, or exactly 13 kilometers north. So if you go this plus this, what you're going to get is a resultant vector right over here. So from the starting tail to the tip of the final value right over there. And you could probably already begin to see what's going on here. If you have a positive value for 13, a negative value for your going south direction right over there, it could be written like this. 13 plus negative 8 is going to give you 5.0 kilometers. And then we need a direction. It's going north. And so your displacement in the end is 5.0 kilometers north, which also, according to this drawing right over here, if you go 8, then 13 north, you're going to get the exact same value. And if you wanted to determine, like based on that formula, what's going on here, well, you would have this point right over here being your initial displacement where you haven't really been displaced at all. So it's your starting value. And then your final displacement is going to be right at the very end over here. And so that's your final value, that's your initial value. So if you go your final value minus your initial value, and your initial value is 0, you're going to get your change in displacement on that fateful Saturday when you were traveling probably in the wrong direction at some point. And this is 5 kilometers above or north of the reference point right over there. So that's how you go about adding the vectors like that. And if we were to use that formula, I verbally said it, so let's just quickly write out what that looks like. Change in displacement is your final value minus your initial value. Our change in displacement in this case, our final value is 5 kilometers north of the reference point. And our reference point, when we initially started, we hadn't changed our displacement at all according to the reference point. And so we end up having a final value also of 5.0 kilometers north, using the formula there as well. You decide to walk to your friend's house. You walk 1.2 kilometers east and then 2.2 kilometers north. What is your distance and displacement? This time around, it seems like you know where you're going, although maybe you would have liked to take the hypotenuse there. Although if you had to walk in, well, if houses were in the way, obviously that wouldn't be feasible or possible. So maybe you're just walking according to the roads here. So let's just assume that. Let's start again with our distance, which again can easily be calculated by just adding these two values up here. So you have 1.2, you have 2.2, you're going to have 3.4, and that's kilometers. And that's it. There's no direction with that one at all. As for your displacement, not sure why we started with that S, it's a little late here, displacement. What are we going to have in this particular one? Instead of adding up any values, because the thing is we really can't do that. We have a value that's going east, we have a value that's going north. So when we were trying to add up components before, in the last lesson, we learned that you have to combine the x values with other x values. You have to combine the y values with other y values. Afterwards, you have your resultant vector where you're going to go tip to tail. So that's what we're going to be doing right now, because we only have two values right over here, two vectors, so to speak here. 1.2 kilometers east. So let's start with that one. 1.2 kilometers east, followed by 2.2 north. And so this one should be a little bit longer. So represented as such. This value is east, it's positive. This value is north, it's going to be positive. So you go this plus this. And again, you could have gone the north value first plus the east value. You would get the same resultant vector. So anyways, we're going to now go, what's your initial value? What's the final value? And so it's going to be your tail to the tip over here. And we're going to want to find this, and we're going to want to find our total displacement as well right over there. So let's start with that. Our total displacement is going to be 1.2 squared plus 2.2 squared, and the square root of that all. Because remember, a squared plus b squared equals c squared. If we just take the square root of this side right over here, it's going to be the square root of these two squareds right over there. Do the math, and you get 2.5 kilometers. And now we need this theta. So same idea. We look over here, we say opposite over adjacent. That's going to give us our tan ratio. And remember last time, I'm just going to go straight to my theta. So I'm going to be taking the inverse of tan of this ratio right over here to find theta. And it's going to be the opposite side over the adjacent side. And our theta comes out to be 61 degrees. So to finally express our displacement, it's going to be that 2.5 kilometers and then followed by that 61 degrees. And if we look over here, it's north of east by 61 degrees. So 61 degrees north of east. And that would be how you'd express your displacement. You have your units, you have your magnitude, you have your angle, and then you have the direction that it's going as well. So all of those need to be included for your displacement. For your distance, all that needs to be included there is just the units for length. So in this case, kilometers. All right. That concludes this short little lesson. Good luck and have fun.